Right now, as you watch this, Europe is sweating through a historic heat wave, and the eastern half of the United States is entering a sweltering, record breaking heat dome. Meteorologists are talking about it, politicians are arguing about it, and every news outlet is dissecting the climate data. But none of them, not one, is talking about the guy from Scranton, Pennsylvania, who proved this was coming 67 years ago with glass flasks on a volcano in Hawaii. This is that story. In politics, they say all roads lead to Scranton, and this city, the electric city, has quietly handed the world more than it ever gets credit for. Today's story is about a man named Charles David Keeling, born April 20th, 1928, right here in Scranton, Pennsylvania. His father was an investment banker, but not just a numbers man. He was a passionate amateur astronomer who set up telescopes in the backyard and taught young Charles to read the night sky before he could read a textbook. That sense of wonder, the idea that ordinary people could measure extraordinary things, never left him. His mother gave him something equally powerful, a love of music. Keeling was so gifted on the piano and the French horn that a professional music career was a genuine possibility. He wrestled with that choice. In the end, science won, but the musicianship stayed. His colleagues would later say he brought the same discipline to scientific measurement that a musician brings to a performance. Everything in its place, every note exactly right. He graduated from the University of Illinois with a chemistry degree in 1948, then earned his PhD at Northwestern University in 1953. His doctoral dissertation, in the dry language of chemistry, was about how minerals crystallize out of natural water. Dry stuff, but it taught him the most important lesson of his career: that precision matters, that the gap between a good measurement and a great measurement could change everything. He landed a postdoctoral at Caltech in Pasadena, and there, under the guidance of geochemist Harrison Brown, he built something nobody had ever built before: an instrument that could measure carbon dioxide in the atmosphere with consistent, reliable scientific precision. Before Keeling, existing CO2 measurements were scattered, inconsistent, and riddled with error. Scientists had rough guesses. He wanted something better. Then he did something wonderfully old-fashioned. He put his equipment in a car and drove. He sampled air at Big Sur on the California coast. He sampled air on the Olympic Peninsula in Washington State. And he sampled air high in the White Mountains of New Hampshire. Remote, windswept places where human pollution was minimal and the air was as clean as it got. And what he found immediately was remarkable. Wherever he had measured, thousands of miles apart, completely different climates and geographies, the carbon dioxide levels were almost identical. The entire global atmosphere shared one consistent baseline number. Nobody had ever proven that before, and it meant something important. If that number ever changed, it wouldn't be a local problem. It would be a planetary one. Roger Revelle, the visionary director of the Scripps Institution of Oceanography in La Jolla, California, heard about Keeling's work in 1956 and immediately grasped its implications. He recruited Keeling to Scripps, where Keeling would spend the rest of his career, and helped him secure monitoring stations through the International Geophysical Year, a 67-nation science collaboration in 1957 and 1958. One station went to the South Pole, and the other went to a summit on Mauna Loa, a dormant volcano on the Big Island of Hawaii, 2 miles above sea level, perched in the middle of the Pacific Ocean, as far from human pollution as you could get on this planet without actually leaving it. Starting in 1958, Keeling's team began collecting air samples every single day. And the method was almost absurdly simple, but the precision behind it was anything but. A researcher would take a football-sized glass flask with all the air vacuumed out, hold their breath to avoid contaminating the sample, walk into the wind, and crack open a valve. The air rushed in. The flask was sealed, shipped to a lab, and analyzed to 6 decimal places of accuracy. Keeling designed every detail of the process himself, and he was famous, some would say infamous, for his obsession with getting it exactly right. If a measurement looked even slightly off, he threw it out and started over. His colleagues sometimes found it exhausting, but Keeling understood something they didn't yet appreciate. This data would only be meaningful if it was immaculate. Future scientists would need to trust every single data point. There could be no shortcuts. By 1960, Keeling had enough data to see 2 clear patterns, and both of them were world-altering. The first was almost poetic. The Earth was breathing. Every spring and summer, as plants and forests across the northern hemisphere burst into photosynthesis, they pulled carbon dioxide out of the air, and CO2 levels dipped. Every fall and winter, as those plants died, decayed, and released their stored carbon back into the atmosphere, the levels climbed again. It was a seasonal rhythm, a planetary heartbeat, visible for the first time in a graph. No scientist had ever seen it before. Keeling had essentially drawn a picture of the Earth inhaling and exhaling. But it was the second pattern that made his hands tremble. Underneath that seasonal breathing, the baseline CO2 level was rising every single year. Steadily, relentlessly. There was no ambiguity about the source. The Industrial Revolution had been pumping carbon dioxide into the air for over a century, and the atmosphere wasn't absorbing it. It was accumulating. When Keeling first set up his equipment in 1958, CO2 stood at 315 parts per million. By 2005, when he died, it had climbed to 380. Today, right now, as you watch this during one of the hottest summers on record, it sits above 424 parts per million. That line has never come down. Not once. Not for a single year. And the world named what he had drawn the Keeling Curve. You would think the scientific community would have thrown a parade. They didn't. In the early 1960s, the National Science Foundation cut his funding. They declared his measurements, and I want you to sit with this for a second, routine. Like the most important environmental data set ever collected was roughly equivalent to reading a thermometer on your porch. His colleagues dismissed him as a glorified data collector, too obsessed with repetition to do real science. In a culture of academic research, novelty was everything. You were supposed to ask a question, answer it, and move on. Keeling's work, measuring the same thing the same way every single day, decade after decade, looked to his critics like intellectual stagnation. It nearly broke him, financially and professionally, more than once. Funding crises came in the 1960s, then came again in the 1970s, again in the 1980s, and again in the 1990s. Each time, he was dragged before skeptical bureaucrats and forced to justify why the same measurement needed to continue year after year. His colleague and Nobel laureate Melvin Calvin once told him he was wasting time. Keeling had sleepless nights well into his 60s, worrying the funding would disappear and the record would be broken forever. Each time he made the same argument. The measurements only mean something if they never stop. A gap in the record would be like tearing pages out of the only copy of the most important book ever written. The data isn't telling us the answer. The data is the answer. Here's the brutal irony, though. Even while cutting his funding, the government used his data freely. A 1963 NSF report warned about heat-trapping gases in the atmosphere using Keeling's numbers. A 1965 report from President Lyndon Johnson's Science Advisory Committee, the first official U.S. government warning about human-caused climate change, cited his work as its foundational evidence. They didn't want to pay the scientists, but they were perfectly happy to use the science. The director of Scripps, Charles Kennel, would later compare Keeling to Tycho Brahe, whose obsessive planetary measurements gave Newton the data to discover the laws of gravity, and Albert Michelson, whose speed of light measurements helped give Einstein the foundations for the theory of relativity. 3 moments in history, he said, where one scientist's maniacal commitment to precision measurement changed the direction of all of science. Real quick, if you're learning something new about what Scranton quietly gave the world, hit that subscribe button right now. We tell new, untold stories every single week. All roads lead here. The Keeling Curve is now engraved in bronze on a building at Mauna. It's carved into a stone wall at the National Academy of Sciences in Washington, D.C., directly across the street from where lawmakers still argue about whether to act on climate change. The BBC listed it as one of the most recognizable scientific graphs in human history, in the same conversation as E equals mc squared and the double helix. In the 1960s, a young Harvard student named Al Gore sat in a classroom and watched a professor project the Keeling curve on a screen. That professor was Roger Revelle, the same man who had recruited Keeling to Scripps. Gore later said he marveled at it. That image planted a seed that never died. In 2006, Gore built the centerpiece of his documentary film, An Inconvenient Truth, around the Keeling Curve, and won a Nobel Prize, partly for bringing that graph to the world's attention. In 1997, Vice President Gore presented Keeling with a Special Achievement Award at the White House. In 2002, President George W. Bush, despite his administration's complicated relationship with climate science, awarded Keeling the National Medal of Science, the highest honor the United States gives for lifetime scientific achievement. And in 2025, 20 years after his death, the International Astronomical Union named a minor planet in his honor, asteroid 284054 Keeling, a lump of rock and ice drifting through space between Mars and Jupiter, carrying the name of a man who stood on a volcano and measured the air. The measurements at Mauna Loa have never stopped, not for a single day. His son Ralph Keeling now leads the same program at the Scripps Institution of Oceanography. It is the longest unbroken environmental data set in the history of humanity. And it exists only for one reason: because one obsessive, chronically underfunded, frequently dismissed scientist from Scranton, Pennsylvania, refused to stop counting. Charles David Keeling was born here in 1928, in the same Scranton now celebrating its 160th year, in the same country marking 250 years of independence this week. He worked with nothing but glass flasks, a custom-built instrument, and an unshakable conviction that the truth was in the numbers. And he proved, decades before the rest of the world was ready to hear it, that we were changing the chemistry of the atmosphere of the entire planet. That rising line he drew, patient, meticulous, relentless, just like the man himself, is still climbing today. And right now, as heat waves bake Europe and a heat dome settles over the eastern half of the United States, that line is the most important graph in the world. and it started in Scranton. From factory floors to Hollywood fame, from the White House to the office, this is where local meets global. I'm Miss Scranton, and this has been All Roads Lead to Scranton. Stay cool, my friends, and I'll see you next week.